We are in chapter 7, which is exponential growth and decay. Well, the first day is. This unit is all about growing exponentially or decreasing or decaying, and the inverse function of those as well, called logarithms. So we'll start with example 1. Bacteria reproduce or grow in numbers by dividing or splitting. The total number of bacteria at a given time is referred to as the population of bacteria. When bacterium in a population divides, the population triples, for this example. Assume the entire population triples every hour and complete the table. So in the first hour, if you triple it, it's going to be 75. And then you triple it again, it's going to be 225. And then you triple it again, and it's going to be 675. And you triple it again, and it's going to be 2025. Now n, okay, after n hours. We don't know, but there has been a pattern throughout all this that you keep that original 25, and all you're really doing is hitting times 3 over and over again on your calculator. So how many times 3's are there going to be when you get to the n button, or n hours? Well, there's 1 3 hours for 1 hour, there's 2 for 2 hours, 3 for 3, so it's going to be 3 n times. So it says write an algebraic expression that represents the population of bacteria after n hours. So 25 tripled n hours. So you have your original population, you have your multiplier, and you have time. It says use your algebraic expression to find the population of bacteria after 10 hours and after 20 hours. So after 10 hours, what is it? And after 20 hours, what is it? It's 25 times 3 to the 10th. That's a lot. That's 1,476,225,000. Okay, and then 25 times 3 to the 20th. It's so big, it's about scientific notation. So the whole point was seeing what a difference it is exponentially, how quickly it grows with not that much time. It says, suppose the initial population of bacteria was 75 instead of 25. We're just going to do 10 hours. So if it was 25 times 3 to the 10th, we know that is 1,476,225. But if we started out with 75, what difference would it make then? 4,428,675. That is a huge difference. Huge difference. Okay. So knowing what your population is, or like an investment, the more you can start out with, the better. Okay. Or just see how big it grows when you begin with something a little bit bigger. It says the population after n hours can be represented by an exponential expression. It says this expression is called an exponential expression because the exponent in it is a variable and the base 3 is a fixed number. The base of an exponential expression is commonly referred to as the multiplier. So when we say this 3 is the base, it's the multiplier. So when we're tripling here, it's 300%. It says example growth 2. Suppose you invest $1,000 in a company's stock at the end of 2005. And the value of the stock increases at 15% a year. Predict the value of stock to the nearest tenth at the years of 2010 and 2015. So you start with $1,000. You have your multiplier, and you raise it to, you go to 2005 to 2010, which was 5 years. And then you also go till 10 more years. If it's 15%, we're not going to multiply by 0.15. So when you make a percent into a decimal, think of that Beyonce song, to the left, to the left. I know you guys are cringing, but you'll remember it. So we're not going to multiply by 0.15 because that would just give you 15%. I want to keep the 100% I have and the 15. So if there is growth, you take 100% for what you have and 15% for growth, and then that's what you get. So 1,000 times 1.15 to the fifth. That's going to give you about $2,000 just sitting there for 10 or for 5 years. Now, if you wait a little bit longer, it's going to be 4,000. 4 times the money. Okay. So that could be for an investment, or if you have a loan that was $1,000 and it was 15%, it's gone to 4,000. But that's if it's simple interest, not compounded interest. And we'll talk about that shortly. Okay. So that's not like credit card debt or anything. That's compounded interest. This is just simple interest. Okay. The next page is decay. So this is what we talk about with like cars. Okay. This one's vitamins. So when you take a vitamin or any form of medication, so people that are going into the medical field or nursing, this is what you need to know. It leaves your system after so much amount of time. Here it says a vitamin is eliminated from the bloodstream, not all vitamins, it's saying a vitamin, at the rate of 20% per hour. The vitamin reaches a peak level in the bloodstream of 300 milligrams. Predict the amount to the nearest tenth of a milligram of the vitamin containing or remaining 2 hours after the peak level, and then 8 hours. So your population to start with, I just skipped an example 3, so we'll start with this. We'll start with 300 milligrams is what the patient had or the person had, and then you're leaving 20%. Okay, so that means 80% remains. So when you're decaying or losing, you take your 100% of what you have and you're losing 20 to the left, So you're multiplying by 0.80. So after 2 hours, how many milligrams is left? And then after 8 hours, how many milligrams is left? 192. And then after 8 hours, 50.4. I round to 0.4 for in the medical industry because you don't want to round down, you want to round up. But if you put 0.3, that's fine too. So that's how many milligrams are left. Okay, but let's go back up here. Suppose you buy a car for $15,000. Now, we were talking about cars in class today. You're not going to find a brand new car for $15,000. Cars are so expensive. So it's probably a used car, but the values of cars decreased very quickly. So they're really not an investment because they're decaying, they're decreasing in value. So we talked about cars and how if you want to buy a new one, great. We're just talking about mathematically the values and what's best. It decreases at a rate of 8% per year for that make and model. Each ones are different. Some, they decrease about like 19% their first year and then slowly like an 8% the other years. It just depends on the car, the make and model. This is predict the value of the car to the nearest tenth of a cent, 4 years and 7 years. So $15,000 was the car. It's decreasing 8%, so that leaves you with 92%. And you want to know how much that $15,000 car is after 4 years and after 7 years. So cars are not an investment. They depreciate in value. So after 4 years, your car is down to $10,000, and that's actually pretty good because you're not losing 8%. You're usually losing more. This is just made up for the example. After 7 years, your car's worth only $8,000. Okay. So this is an example of decay. So the first one, it was exponential growth. And this one, you have a lot of money and then it's not worth a lot of money. Okay. We're going to talk about the graphs in a minute, but we're going to do a midpoint check. So let's just reiterate. A rate of decay can be thought of as a negative growth rate. To obtain a multiplier for a decrease, subtract the rate of decay from 100. So if you're decaying at 30%, 70% remains. Okay. So find the multiplier for the growth or decay. If you have 7% growth, you have your 100 plus your 7 is 107 to the left, So your multiplier is 1.07. Pause the video and complete B, C, and D. Okay. Number 2 says, write a model for the following situation and predict the population for a time period. Try pausing the video, completing the 2A and B, and then come back and look. They want you to write a model, so you did. And then after 8 hours, what's the population? So you started with 125, and now you're at 32,000. See how high that jumps? That's the exponential growth. And now you have 775 bacteria that triple every 30 minutes. And then they want 4 hours. Well, if they want hours, how many 30 minutes are in an hour? There's 2 30 minutes in an hour. So 775 times 3, how many 4 hours with every 30 minutes? It's doubling. Some people just put it to the 8th, but that's where it comes from. You're going to get 775 times 3 to the 8th. Now you could stop right here if you wanted to and try it again in your review packet at the very end, because you're going to hand that in. And then you could come back. Or if you want to wait, you can do that too. All right, now we're going to look at graphs. Okay. It says the function of an exponential graph with base of b, where b is positive. B is a positive real number other than 1, and x is any real number. So it says make a table of values. Okay, when you graph any function, you're going to put in negatives and positives. So I'm going to put 0 in the middle. I'm going to try 1, 2, 3, and 4, and -1, -2, and -3. Okay, 2 to the 0 power is what we're doing. 2 to the first power, 2 to the second, 2 to the third, 2 to the fourth, 2 to the negative first, 2 to the negative second, and 2 to the negative third are what you're going to do. Okay, so this is going to be 1/8, 1/4, 1/2, 1, 2, 4, 8, 16. So when we go to 4, we're going to get 16. Oh, that's way up here. When we get 3, we're going to go to 8. 2, it's going to be 4. 1 is 2. Oops, 2. 0 is 1. -1 is 1/2. -2 is 1/4. -3. Oh, we're getting lower and lower. We're not going to get quite to 0. Will we ever get to 0? No, we're just going to get really small, 1 over a million, okay? It says notice that the x values decrease, the y values get closer and closer to 0. An asymptote or asymptote is a line that a graph approaches but does not reach. For y equals 2 to the x, the asymptote, well, it's left to right, so it's a y equals, and you don't go past 0, so y equals 0. Okay? It says below are 3 exponential models. Graph the functions using a graphing calculator. How are they the same? How are they different? So if you graph each one, it's going to kind of look like this. One's kind of here, and that's 1.5 to the x. But then you notice it gets a little steeper. Oops. And it gets a little steeper. And then it gets more steep. Well, yeah, because if your base is bigger, you're exponentially growing. But they all intersect at 1 point, 0, 1. Because when you put anything to the 0 power, it's going to give you 1. So for what value of x are they all the same? 0. Okay, for what value of x is this one the greatest. So when the numbers get to be more positive, this is true. And when the numbers are negative for x, this is true. Okay, you can see it better on your graphing calculator. If you type all three of these into y equals, you put them in, and then hit graph 3 to the x, to the x, to the x, you will see in different colors too for this one. It's kind of cool. So you'll notice that 1.5 is lower when these values are great. You can't see here, but think about it logically. If I have negative values, what are your answers? Okay. Next page. It says graph 1/3 to the x, 1/2 to the x. So let's try opposite now. 1 divided by 3 to the x, 1 divided by 2 to the x, 1 divided by 1.5 to the x. That's the 1/3. That's the 1/2. That's the 1/1/5. How are they related? They share the same intercept again. They all go through that 0, 1. How are the bases related? Well, the steeper one is the blue one, which is 1/3. It's actually the steepest. Well, think about it. 1/3 is about 33%. If you're 33%, that's actually a decay of 67. When you're 1/2, that means you're decaying at 50%. And when you're 1 divided by 1.5, you're at 67%, so you're decaying at 33. So this is a slower decay versus the higher decay of 1/3. Okay? It says, for what values of b's does the graph rise from left to right and right to left? So we're going from left to right here because they are when b is less than 1. And so when b was greater than 1, it went up like this. When it was b is less than 1, it went down like this. Okay. It says exponential growth and decay. And they just reiterated it here. When it's greater than 1, it's growing. When it's less than 1, it's decaying. Okay. And then we're going to talk about compound interest tomorrow. Compound interest. Okay. Which is when interest is added to the principal so that from then on, you're paying interest on your interest. And we're going to talk about this tomorrow. So that's why people get into credit card debt or student loan debt, because you're paying money off of that interest. So let's talk about that in the next lesson. Today was graphs and exponential growth and decay and multipliers.